Hello everyone. Once again, I welcome you back in the course on manufacturing method. In the previous classes, already we have had the general introduction and different types of categories of manufacturing processes. So various materials which can be processed by various processes. Similarly, the casting, what is casting, what are the steps involved, what is the typical foundry process, its capabilities, advantages. Similarly, different casting, we can say cast part examples and all. So those things we have already discussed. We have seen that from right from the very big to the very small parts can be casted. Similarly, different categories of casting process like expandable mold process, permanent mold process, those things we have already discussed, and we know about getting ratio now. And in the last class, basically we have discussed about the solidification of metals. Okay, in that particular case we have discussed about the solidification of pure metals as well as solidification of your alloys. In those cases, basically the you can say the cooling curve associated with both the cases, those things we have discussed, and what are the basic characteristics like solidification happens at a constant temperature in case of our pure metal as well as eutectic alloys. Similarly, solidification happens over a range of temperature in case of alloys. Those are the things we have discussed. Similarly, the grain growth, in which direction grain occurs and all, how solidification starts, those things already we have discussed. Okay, so towards the end of the last class we have basically discussed like there are certain problems like the massy zone is there in case of our solidification of your uh, alloys. Okay, so in that massy zone basically it's kind of a zone which is paste like. Okay, and why it occurs, so actually whatever the dendritic structure it gets developed during the solidification purpose process, as the whole solidification happens within a temperature range. So at certain time we have certain grains, okay, which are solids. Okay, and similarly it entraps those dendritic structures, it entraps certain liquid island or liquid region also, so we get some massy zone. Okay, so there are certain one we have already said that some liquid solid liquid interface or solidification font it gets developed in case of solidification of your alloys. That has to be properly investigated, and the knowledge of this we must have. Okay, so later on we'll discuss about some center line shrinkage and what is CFR ratio. Those things we'll discuss later on. But in the you can see that the presence of solid crystals ahead of our the presence of solid crystals ahead of solid liquid interface, it makes the feeding of the liquid metal more difficult. Okay, so and this leads to greater risk of having voids within the casting. Okay, and it is associated with the center line shrinkage. Okay, so this is one of the problem, and those things we have to take care of. Now whenever we are discussing about solidification, so then we must know, if we are talking about a particular type of cast of a particular design, particular shape, then what is the solidification time, how can we obtain the solidification time, because then only we should be able to like know. That means if you are talking about a particular industry or processing unit, so at a particular time how much productivity we can have. Similarly, we must have the complete solidification and cooling down of it. After that only we should, if it is expandable mold process, we have to break the mold, take out the cast and all. Otherwise, if the solidification is incomplete and if you try to break the mold and take out the part, then definitely the whole thing will be kind of a wastage. So this is also very important, we must know about the solidification time. Okay, now this total solidification time, it is the time required for the casting to solidify after we pour it. Okay, so basically this is dependent on the size and shape of the casting, and this is given by an empirical relationship known as the Chvorinov's rule. And what does it states? It states that total solidification time TTS, it can be given by a multiplication of this cm. Cm is a mole constant, okay, into V by A, that is volume of the casting, by the area, surface area of the casting, to the power certain one or exponent, that is n. Okay, so Ts equal to TTS, that is total solidification time, it is Cm into V by A to the power n. This n generally we consider as 2. So while solving problems and all, directly it becomes solidification time is some constant mole, that is the moles constant V by A whole square. Okay, so directly we can use this. Okay, so one thing you must remember is this TTS, that is it is total solidification time, not the local one. Okay, and similarly it is given in minute, and this volume of the casting will be considering in centimeter cube for this empirical relationship. Similarly, area, surface area of the casting in centimeter square. Okay, so and cm is moles constant. This mole constant, it depends on the various conditions of the casting operation. Okay, like the mole material also it is dependent on, because depending on the mole material, specific heat of it will be different, the thermal conductivity of different metals will be different and all. Okay, and the cast, about the cast metal also similar is the case here. Also thermal conductivity will be different, what is the heat of fusion it takes place inside, so based on that it is different. Okay, but it is a constant for a particular time. Okay, for it. So this is the formula, very easy one. Okay, and very versatile, useful one. This you must remember. So later on we'll be solving some problems related to this, but not in this class. Next, whenever we are talking about solidification, then one thing we know is that we want that our mole should solidify proper in a, not the mole, the cast should solidify the molten metal, that means in a very proper way. And we already know that, we have already discussed, that means during our solidification process, during solidification of metal, basically this metal shrinks, that is the volume goes down. And we already know that we always incorporate riser in the mold design so as to like compensate for this kind of shrinkages, solidification shrinkage and all. And what basically is there, the same molten metal it fills the riser. Okay, and now what is our intention, whenever, that means your where the molten metal is going inside the mold cavity, so within the mold cavity basically we want that it should solidify. Yes, and now whenever there is shrinkage, what is our intention, from the riser, the riser should be able to provide molten metal. That means we are working with the same flow of metal. Yes or no? Because it will only get filled, like the riser will be getting filled by the same metal which is going to fill the mold cavity. Okay, now if the riser has to provide certain molten metal to compensate for the solidification shrinkage, so in that particular case, what is the main criteria, to perform its function of feeding molten metal to the main cavity, the metal in the riser, it must remain in liquid phase longer than that of the casting. That means casting will solidify, after that only we want that the whatever riser metal is there, that should solidify. Otherwise, if it solidifies at the same rate, or maybe prior to the solidification of the mold, main one. Okay, not the mold, but that particular cast part. Okay, that cavity, mold cavity, whatever is being filled up. Okay, so in that particular case it is not going to serve its purpose. So what is our main thing is, in other words, the total solidification time for the riser, it must exceed total solidification time for the main casting. So sometimes in some competitive exam this kind of problem are being asked, so those geometry will have, from the geometry, and cm will be generally provided, that is the mole constant, v, that is the surface volume of the casting, as well as area, surface area. Those things very easily from the geometrical relationship anyone can find out, and to the power t2 that is there. Okay, so from there we can find out tts, that is the total solidification time for both the cases, that is for the mole. Okay, or the, you can say the cast ultimately. Okay, or that particular riser. So after that we can find out whether that riser design is feasible or not in terms of solidification time. Okay, this mole constant for this both the cases will be same. Next we are going to discuss about the center line feeding resistance, or CFR. In short, it is CFR. So it's a problem, or it's a situation associated with this, you can say, solidification of moles. So now what basically happen is, so we already have discussed about chill. Okay, I told you to go through the different like parameters, or not parameter, different terminologies involved, like the chill, the riser, the mold, or different patterns, etc., etc. So now we already know that we use some external or internal chill for proper directional solidification purpose. Okay, and now in that particular case, the freezing pattern of an ordinary and a seal mold, they are different. Right now we are talking about mainly sand mold and all, which is one of the most versatile one. Okay, sand casting. Now, in basically, what is the problem, or you can say what is CFR? Basically, in an ordinary sand mold, the solidification it starts at the center line of the mold before the solidification is complete, even at the mold phase. So, from this particular left figure, all of you can very easily see. Okay, so what is basically happening along this axis? We are showing the distance from the mold, and this is mold center line. Okay, up to half of the portion we are drawing, that means, and this side we are showing the line. Okay, now what happens, this line shows the starting of freezing at different levels means at different distances from the mold phase. Okay, and this line shows at that particular different distances when solidification is over, that is the end of freezing. Okay, so now what we have seen here, this is the freezing diagram. Figure A is freezing diagram for ordinary sand mold, and second one is with a chill mold. That means we are providing or we are using chill. Okay, so now basically what happens, so in an ordinary sand mold, that is the left figure, the solidification it starts at the center line of the mold before the solidification is complete, even at the mold phase. Okay, now at the mold phase where the solidification is complete. And similarly, you can say in case of chill mold, I am going to discuss both of them together. In case of chill mold, on the other hand, what happens? As we are talking about chill mold, that means we are using some chill. Okay, that means at that particular portion, it is generally like the chill are generally some metal elements and all. Okay, metal parts we generally use. Okay, and now in that particular case, at as these are cool parts, okay, cool position, so at that particular position, due to rapid heat extraction will be there. Okay, so due to this rapid heat extraction, a narrow liquid zone or liquid solid zone, it quickly sweeps across the molten metal. Okay, now here you can see, now in this particular position it shows that at this particular mold center line, here at the center line, it has started, the start of freezing it has occurred. Okay, and by that time when it has started freezing at the mold center line, due at that time, if you consider the phase, that is distance from mold, here phase it is, here it is almost zero, that means at that particular position only, here still it has not solidified. Where it is getting solidified, it is solidifying here after, suppose this is up to 10 seconds. Okay, but here suppose it is 8 seconds. So in that particular case, at 8 seconds itself, in the mold center line, it has started solidifying, start of freezing. Okay, but by the time up to 8 seconds, at the you can say mold zero position, that means zero distance, it has not even, solidification is not even completed. Okay, so that means what basically happen in most of the cases, we feed the molten material, we generally feed the molten material in such a way that, that means, you already know, so there are two halves generally in the mold. One upper half is the cope and the lower half is the drag. Okay, and generally feeding occurs, feeding happens at the center line in most of the cases. Okay, now center line itself, if it is kind of solidified, then feeding of liquid metal will be very difficult. So that is what is the problem associated in case of sometimes with the ordinary sand mold. Okay, but this problem, if we use the chill, it is not prominent, as can be seen from the second figure. Okay, I hope you have understood. And in between, definitely during the process of solidification, there will be liquid plus solid region inside. Okay, because start of this is the start of freezing, okay, this line, and here it ends freezing. So in between it is solid plus liquid interface. Okay, I hope you have understood. So this particular CFR, how can it be given as it is CFR equal to time interval between start and end of the freezing at the center line divided by the total solidification time of casting multiplied by 100%. So in this particular previous figure, AC by OC, that is this AC by OC, okay. So it this particular thing multiplied by 100% gives you the whole central. And now if CFR is it's greater than 70%, feeding is generally considered to be difficult, and that's why the knowledge of this sealing behavior and what is the CFR, it is important. Otherwise, if in your case of in your design, if CFR becomes more than 70%, it will be very difficult to feed that particular molten metal to the mold cavity. And if the feeding itself is not good, then definitely there will be some, you can say, parts, positions where there will not be any, you can say, liquid metal. It will not cover that particular position, fill the particular position, and if it has not filled this particular position, there is no question of getting the solidification there and getting the proper shape. Now these all things we are discussing all the time. We are discussing about shrinkage, and shrinkage. Okay, so now what kind of shrinkages, what are the different stages of shrinkages that we generally see, that we'll see. Okay, so this metal generally shrink during solidification and while cooling to room temperature. So definitely solidification also, during solidification also it will shrink, and at solid temperature itself, whenever it is cooling down up to the room temperature, then also it will shrink. And now this shrinkage, the causes, it generally causes sometimes dimensional changes. Okay, because previously whatever dimension we had, due to shrinkage, definitely there will be deviation from the proper previous dimension, and sometimes some warping and cracking etc also occurs, also happens because of this shrinkage, abnormal shrinkage. Okay, and generally there are these three subsequential events, sequential events that are there. The first one is contraction of molten metal as it cools prior to its solidification. If you can recall the cooling curve, there you have seen three basic parts. Okay, we'll go back to the previous. Okay, suppose this one. So here you have seen there are three types of contraction during solidification. One is during the liquid cooling zone itself. That means it is now at liquid zone. Okay, liquid state itself, but it is cooling down, so there also we can expect some contraction. Similarly, when latent heat of fusion is giving off and phase change is happening, then also there will be shrinkage or contraction. Similarly, at the during solid cooling also we can expect some solidification, the contraction. Okay, so this is the three subsequent stages are involved. So contraction of molten metal as it cools prior to its solidification. Next, contraction of the metal during the phase change from liquid to solid, and during that time latent heat of fusion is being given off. And contraction of solidified metal, that is the casting or the cast, as the temperature drops to ambient temperature in the solid state itself. Okay, and now out of these three stages, the largest potential amount of shrinkage it occurs during the cooling of the casting to the ambient temperature, that is the during the solid cooling. Okay, now there is one exception. Okay, we already know for compensating of this particular shrinkage we already have riser and all. Okay, so that's why once again the riser design itself, whatever we have previously studied in material manufacturing technology, that is also, that itself is a task in casting. Okay, so now one of the exception you must know, and sometimes these are asked in like competitive exam. So some metals, like just like the gray cast iron, it expands, okay, in the last stage of cooling of solidified casting. Okay, so it is kind of exception. Generally we know all the metals basically during solidification it contracts, but gray cast iron it expands in the last stage of cooling of solidified casting. The reason is graphite, which is a, you can say, in gray cast iron there will be that difference between graphite is there, is that the graphite has a relatively high specific volume, and when it precipitates as graphite flakes, during solidification of the gray cast iron, it causes a net expansion of the metal. So basically the graphite flakes are responsible. Just like you have corn flakes and all, you already know the volume of corn flakes with respect to the corn. If you consider, the volume is more. So similar is the case here. Some graphite flakes we obtain, and it actually causes net expansion of the metal. So because of this, see, generally in the third stage the main riser consideration comes. Okay, third stage means during the solid cooling, or you can say solid contraction time. Now because of this, as at the end stage, okay, what is basically happening, previously in the first and second stage, whatever contraction it has happened, in the third stage, that is the contraction of solidified metal, in case of contraction, in case of gray cast iron, it is expanding. So it compensates both the kind of contraction that already we had, and it like nullifies that. Okay, and because of that, sometimes risers even may not be necessary in case of casting with gray cast iron. So this is sometimes it asked in the competitive exam. Okay, and definitely we already know we want directional solidification, and proper directional solidification it's desired to minimize the damaging effects of shrinkage, and for that we use internal seals or external seals, etc. So in the, for today we complete here, and in the next class we'll be discussing basically about the melting furnaces. That means the if we are talking about casting, then definitely we have to hastess itself is to melt the metal, and now for that different melting furnaces we use. So this in melting furnaces in brief we'll be discussing in the next class. Okay, thank you.